Man has always been challenged by the need to build bridges to carry his roads over rivers and gorges. In New South Wales, the Hunter River and its many tributaries have presented many such challenges to our road builders. Over the waterways in the Hunter Valley, there are hundreds of bridges, large and small, old and new, built of timber or steel or concrete. This is the newest and biggest of them all, the Stockton Bridge, a challenge that has been met and won. As the Hunter approaches the sea, with Newcastle at its mouth, the river divides into two channels, forming Kooragang Island. Until recently, the road route from Newcastle to its northern districts has involved a considerable detour inland as an alternative to a vehicular ferry service between the city and Stockton. With the growing importance of Newcastle and the rapid industrial development in the area, including Kooragang Island itself, the volume of traffic was increasing beyond the capacity of the vehicular ferry service. The new Stockton Bridge over the north channel of the Hunter River provides a much improved route from Newcastle to its northern districts and eliminates the need for the ferry, a saving of $750,000 a year. The bridge, designed by the Department of Main Roads, is 3,358 feet in length and comprises 8 approach spans over the land on each side of the river and 7 main spans across the river itself. The central span is 270 feet long and provides 100 feet vertical clearance for shipping. The bridge is founded on board piles embedded in rock at depths ranging from 70 to 140 feet. Building of the piers for the approach spans began in 1968 on piles already constructed by the department. Each of the approach spans comprises 11 pre-stressed concrete girders, which are connected and supported by a pre-stressed concrete cross girder at the pier. The approach span girders are made up of precast concrete segments, 6 to each girder. These segments were manufactured at a casting yard 20 miles from the bridge site. On arrival at the site, the segments were assembled into girders. After the placing of joint concrete, the segments were pre-stressed with cables which together provided a stressing force of 300 tons per girder. The completed girders were then loaded onto rail trolleys and hauled up the embankment to the bridge. The girders were erected with the aid of a steel launching truss. Concrete was cast in place between the flanges of the girders to complete the approach span deck. The piers at the water's edge were constructed as reinforced concrete skeletons, which were later clad with precast concrete slabs. These hollow piers provided access for water, gas, telephone and electricity mains which crossed the waterway in the main spans of the bridge. The construction of piles for the piers supporting the main spans started with the driving of steel casings to rock. These casings were assembled in 90 feet lengths on the shore and driven with a diesel hammer. After driving the initial 90 feet, further lengths of casing were welded and driven until the casing reached rock. Rock sockets were drilled with a rotary bit, the drilling being washed out with a continuous flow of water. Steel reinforcement was assembled into cages and placed in the piles by crane. The piles were then cleaned out with an airlift pump in readiness for filling with concrete. Concrete was placed in the piles underwater by the Tremie method. The Tremie pipe was made up in 10-foot sections, the bottom being always immersed in concrete during the pour. As the pipe was raised, sections were removed progressively from the top. Each cluster of piles was surmounted by a reinforced concrete pile cap, on which was constructed the single column pier. Each of the main spans comprised two pre-stressed concrete box girders, connected by precast concrete top and bottom slabs to form a 3-cell spine beam. Steel falsework was assembled between the piers to support the girders during construction. Box girders for the main spans were constructed from segments manufactured on the site. These were transported by a Goliath crane and barge. The segments were erected on the falsework by a floating crane, the position of all segments being carefully checked before the placing of joint concrete. Each completed girder was pre-stressed by 13 high tensile steel cables, which together provided a force of 5,000 tons. After tensioning, the cables were encased in concrete and the ends sealed. The main spans were constructed progressively from both sides of the river. The gap was finally closed with the construction of the center span. The space between the two box girders was connected by the placement of top and bottom slabs, both precast on the bridge site, thus completing the spine beam. To complete the deck on the main spans, precast cantilever slabs were attached to the spine beam. The cantilever slabs were held in position by falsework beams until attached to the spine beam by stressed high tensile bars. On the extremities of the cantilever slabs, heavy concrete crash barriers were provided. The concrete was steam cured to speed up the work. Travelling formwork was used for the construction of the median strip to separate opposing streams of traffic and to serve as a footway. The structure neared completion with the erection of double steel pipe rails on the crash barrier, railings on either side of the median strip footway, and the installation of lighting. Meanwhile, work on the approaches was proceeding. After the application of a tack coat of bitumen, asphaltic concrete was laid to provide a smooth running surface. Landscaping, lighting, and finally line marking completed the work on the approaches. And so the Stockton Bridge was finally ready for traffic. In its construction, 23,000 cubic yards of concrete were used, together with 600 tons of high tensile steel and 2,500 tons of steel reinforcement. On November the 1st, 1971, a large crowd gathered for the opening ceremony, which was introduced by the Commissioner for Main Roads, Mr. R.J.S. Thomas.
Newcastle has always been a leader in coal, the steelworks, and secondary industry, to which today is added a great bridge. One of our country's longest, and in this state, second only to the Sydney Harbour Bridge.
The Premier of New South Wales, the Honourable R.W. Askin, MLA, then addressed the audience.
It will be the pleasure of each and every one of us here today, in the times ahead, to be able to say that we were associated with the opening of this great public facility here, the Stockton Bridge. It is now my very real pleasure and privilege, ladies and gentlemen, to officially declare the new Stockton Bridge open.
The Premier cut the ribbon to open the bridge and unveiled a commemorative plaque. Meanwhile, the Kundaloo, representing the three ferries now supplanted by the bridge, paid a ceremonial visit to the site before going into well-earned retirement. Stockton Bridge, the longest so far built by the Department of Main Roads, takes its place with other great bridges as a symbol of the dynamic progress being achieved in the network of main roads in New South Wales. This graceful bridge and its approaches, costing $6.5 million, provide a vital link in this network of road communications. For the many travellers over the Hunter River, a new era begins.